don't want to waste time searching in a very large window, typically a reasonable size window. We'll talk about the size of the windows a little bit later on. But, and I have a slide showing you the trade-off between the size of the windows, is the size of the search window, and the bit rate, or the quality. Okay? And you will see that you trade off very, very little. Okay? Now, how do we know that one guy is the best match of the other? We need to come up with a criterion, right? And the criterion, there are typically two types of criteria that we use here. But the most popular is called sum of absolute difference, or SAD, or MAD, or whatever name that we called it before. This is the L1 norm of the red square and the yellow square. Okay? So what happens is you take the current block right here, you take the difference between the block in the reference frame, take the absolute value, sum them all up. Okay. Now, this is, and you have to search, okay, the index here from 0 to Rx and 0 and 0 to Ry is the size of the block. Okay? So here, this is the size of the block, Rx, Ry. Okay? And then you have to slice this box all around, and the guys that give you the lowest SAD win. The guys give you the lowest SAD win. That's it. Okay? Is that clear enough? Okay? If you find the lowest SAD, okay, so first of all you have to check here, right? You check here. You check all over the place. Okay? You find the values that give you the lowest SAD, and then you declare this the dx, dy that you find as the motion vectors. Okay? You declare that the motion vectors. Okay. Now you can modify this a little bit, and instead of using L1 norm, you use L2 norm with a square here. Okay. It turns out that it doesn't make that big of a difference. Okay. But in some architecture, you are paying for this, right? Because you have to do multiplications, and in some, I think in Intel architecture, it doesn't make any difference at all. But typically, this is less complex than that, for sure. Now, people have tried other norms, other correlation measure, but roughly nothing really outperformed this simple SAD. Nothing really outperformed that by a significant margin. Okay, so we start with this. Approximately the same coding performance, and this is typically the less complex out of everything that people try. Okay, it's a very simple procedure. Sum up the differences. So the common setting is this. We typically do a macro block has the size of 16 by 16. That's what we will be using all the time. The macro block has a size 16 by 16. Okay, and the search window size is typically 15 here, 15 there. So you will be able to search in a let's see, what, 46 by 46 window. Okay, that's a very typical setting that you would see in MPEG 1, MPEG 2, for example. Okay? Motion estimation only perform on the luminance space. We never do motion estimation for CR and CV. Okay? Because they are correlated anyway. So if you find a good motion vector for Y, that motion vector is also very good for CR and CV. So let's not waste time. Okay? The chrominance is typically has smaller size, so it will be 8 by 8, and we only do motion estimation on this Y block. So let's think about strategy to do this. Okay, strategy to do this. The first is called exhaustive search. That should give you the minimum all the time. Agree? Okay, now let me explain the red dots. I am showing you the possible places for your motion vectors. I'm showing you all the possible placement of your motion vectors. So this is my dx, this is my dy, this is 0, 0. So this, at this location, it means that the two blocks do not move. This location means that the block doesn't move. Okay, the red block and the yellow block stay exactly the same at the same place. This location means the yellow block is 1 pixel over, or the object is moving 1 pixel over. This guy means that the object is moving 1 pixel up. This block means the motion, the block is moving 1 up and 1 sideways. Okay, so on and so forth. So this means that the object is moving very far away, and this means that the object is moving is very close by. Okay, and what you do is you go through every single red dot. For each of the red dots, you have to do that double summation with the absolute values. Okay, come up with one single SAD. Right? So you have one SAD for this guy, you have another SAD for this guy, you have another SAD for this guy, and then whoever has the lowest SAD out of these total wins. Okay? It's trivial, it's very brute force, but actually that's what's being done in practice a lot of the time. Okay? Exhaustive search. Okay? Now, so what is the complexity of this thing? Okay, how many operations do I need to check one dot? How many operations do I need to check one dot? Suppose that I'm going with this guy. Not 64, but 64 is way too small, right? Okay. This is going from 0 to 15, this is going from 0 to 15, okay? Yes, 16 square. 16 square operations, okay? 16 square operations just to be able to find this one single SAD for one block, right? And so to find the motion vectors, for just one micro block, how many do you need? Well, you count how many dots you need, and then you multiply by 256. Agree? Okay? How many dots depends on the search area. Okay? So how many dots do we have in this search area? How many will you be able to have? 30 here and 30 there. Agree? Right? 30 here and 30 there, right? Because you're going to take this red box and put it here, right? And then you move down. How many times are you able to move down? 30. 30. And you'll be able to move over by another 30, right? So 30 squared. That's 900. Almost 1,000, right? And then multiply by the 256 that we need. Okay? For each of the locations that we search, okay? And that is the complexity of one single square. Okay? That is the complexity of one single guy. Just one guy. Okay? Then you have to move on to this one. You have to repeat the same thing again. The entire thing. Okay? And then move to this one, you repeat the entire things again. Okay? And you do it for all the blocks here. So already you should see that this is a tremendously computationally extensive type of algorithm. Okay, it's very costly. Okay, and you have to do what? 30 frames per second. You have to be able to process 30 of these frames per second. Okay,